In this video, we are going to learn the concept of periodic shutdown in ProModel and see how we can implement this concept. So what do we mean by periodic shutdown? So we all have been or have faced systems in, for example, a bank where they start operation from, let's say, 9 a.m. till 4 p.m. But at some point during the day, they may close for lunch break. And during that time, which may be, for example, from 12 noon to 1 p.m., in that 1 hour of lunch break, they do not let any new customer to come to the system, but they still continue working till anyone who is in the system is out. But in that 1 hour of break, they do not let any new customer to come to the system. So if you're modeling a bank in this scenario, we want to still be able to continue running the simulation. We just have to tell the simulation to not to let any new customer to enter the system in that 1 hour, which is considered as the launch time. So these times, for example, the launch break is what we call as a shutdown period in the simulation, where we do not let any new customer to enter the system. Also, after 4 p.m., when the bank closes, again, we do not want to let any new customer to enter the system. We are considered that as a shutdown as well. And we call it periodic because if I'm going to continue running the simulation for more than 1 day, all these shutdown times or the times where we do not want to let any new customer to come to the system are going to be repeated for the second day, for the third day, and so forth, assuming that I want to continue running the simulation for more than 1 day. So all these shutdown times are going to be repeated periodically in the simulation. Now we want to see how we can take care of this periodic shutdown in a simulation model. We're going to develop a simple model. I want you guys to please create a new model in the folder for week 5. We are going to name the model as Bank of America BOA-periodic shutdown. Okay, so this is going to be the name of your model. This is the structure of a model. We have a bank with 3 parallel operators. Customers first go to the entrance. That's our first location. And from there, they go to the queue. There is a queue in the bank. And then from there, they go to any one of these operators and then leave the system. So 3 locations. First, they go to the entrance, then they go to the queue, and then they go to any one of these 3 parallel operators, and then they leave the system. Customers come to the system with inter-arrival time of 3 minutes, exponentially distributed. The time that they spend with the operator is uniformly distributed with average 10 and half with 6. And the bank works from 9 a.m. to 4 p.m. Okay, so this is the working hour of the bank. The bank works from 9 a.m. to 4 p.m. However, at each day, the bank closes between 12 to 1 p.m. for lunch. So that's the shutdown period as well. And also after 4 p.m., again, the bank closes. So we do not let any customer to enter the bank in that period. So we want to model the system. Obviously, the structure of the system is very simple, right? That's something that can be done easily. We just want to learn that in this structure, how we can take care of this periodic shutdown when we know the bank works from 9 a.m. to 4 p.m. for 7 hours. And out of these 7 hours, there's 1 hour from 12 noon to 1 p.m. when the bank closes for the lunch, and we do not let any new customer to enter the bank in that time period. And also no customer can enter the bank after 4 p.m. That's when we close the doors of the bank as well. So I want you guys to please pause the video at this point, create these 3 locations that we have: entrance, queue, and operators. We have 3 parallel operators. For the entrance and queue, pick the capacity of infinity. For operators, obviously capacity is 1. They can process 1 customer at a time. But for entrance and queue, pick the capacity of infinity. For the arrival process, this is what we know, that the customers come to the system 1 by 1. And then the inter-arrival time is 3 minutes, exponentially distributed. So please create the locations, create the entity, customer, and create the arrival, and then we do the processes together. This is the structure of my model. There is entrance, there is teller queue, and then there is operator. There are three operators. For the queue and entrance, I put the capacity of infinity. For the operator, as I said, there are three parallel operators, so I define the unit as 3. So instead of you can also define 3 explicit operator and just take care of the fact that there are parallel operators in the processing. When you define the processing, you can do that as well, or define just one operator and then change the unit to 3, and then the simulation would automatically create 3 operators for you, operator 1, 2, 3 for you. Okay, so for the queue, the queuing rule is first in, first out, but there's no queuing rule for the entrance. Okay. In terms of the entities, I have customer as my entity. In terms of the arrival is simple. Customers go to the entrance, and then they come to the system one at a time from the start of the simulation for as long as we run the simulation. And then the inter-arrival time is 3 minutes, exponentially distributed. Okay, so now let's go to the processing. Okay, so how is the processing? So the processing is, I'm going to use the click method. So the customers go from entrance to teller, right? And then from teller, they go to the operator. And from operator, they leave the system. And the time that they spend with the operator is uniformly distributed, 10:06 minutes. Okay, so that's the time they spend with the operator. And once they are done with the operator, they leave the system. So in this scenario, then customers come to the system from entrance, and then from there, as soon as they come to the entrance, they can enter the teller queue and wait in the queue and then get processed with one of these operators. However, if I just leave this system as is, then during the whole simulation runtime, the customers can come to the teller queue and go get the service. However, this is not the case here. We know that there are specific hours in the day or during the simulation time that I do not want them to let customers to go to the queue. So customers come to the system, so customers get to the entrance, but I do not want to let them to go to the queue, because once they get to the queue and to the operators, that feels like they are in the system, they are in the bank getting the service. However, I don't want that to happen. So right here at entrance, as soon as the customers enter the system, now here I have to write the condition that tells the simulation that look at the simulation time here. If the clock is between 12 noon to 1 p.m., do not let those customers to come in. Also, if the clock is past 4 p.m., do not let those customers to come to the system. So they get to the entrance. Basically the simulation generates those arrivals, but those arrivals do not get the chance to come to the system, to get to the queue or to get to the operators. Okay, so right here I have to write down the condition that says look at the clock at that point, and if I'm during the operation time, let the customer to come to the system. If I'm not during the operation time, if it's during the break time or past 4 p.m., then send the customer to exit. Do not let the customer to come in. Okay, so that's what we want to do. Now let's get a better sense on how potentially we have to implement this in the system. Let's assume this is day 1. So the bank starts at 9 a.m. They continue working for 3 hours till 12 noon. And then from there, we go all the way to 1 p.m. And then this is lunch break. This is break time. And then from 1 p.m., we go all the way to 4 p.m. as well. And that's our work time as well. So the green is operation time and the black is break time. And then at 4 p.m. we close the door, and next day we open the doors and we continue the same. So in day 2, again, we start at 9 a.m. We go all the way to 12 noon. We close for lunch till 1 p.m. We open the doors again and we continue till 4 p.m. Okay, now let's see how the simulation time goes in this scenario. When I start the simulation, the start of the simulation represents 9 a.m., right? That's where the start of the simulation is, when the customers start coming to the system. In simulation time, just the start point, that's equivalent to time 0. That's time 0, okay? And as I run the simulation, when I get to 12 p.m. in the real world, that's 3 hours of simulation time, okay? So that's equivalent to hour 3 in the simulation. So that's equivalent to hour 3 in the simulation. Or if I want to mention that in minutes, that's equivalent to minute 180 in the simulation. Okay. And then I continue the simulation. I get to 1 p.m. That's after 4 hours in the simulation time. So that's hour 4. Or if I want to write it in minutes, that's 240 in simulation time. In the minutes. In minutes. And then when I continue all the way till 4 p.m., by 4 p.m., it's 7 hours simulation time. So I'm in hour 7 in terms of the simulation time. And then in terms of the minutes, that's 420 minutes. So now, if I want to tell the simulation that do not let any customers to come to the system during the break time, during the lunch break time, and also after 4 p.m., all I have to do is to look at the simulation time and check. If the simulation time is between 180 minutes and 240 minutes, that means I'm between 12 noon till 1 p.m. in the real world. In that scenario, I do not want to let any customer to come to the system. Also, I have to look at the simulation time. If simulation time is greater than 420 minutes, then I also do not want to let any new customer to come to the system at that point as well. So then I can write this condition as if simulation time. So if I want to get the simulation time in ProModel, I have to use the command clock. And here I can, if I write clock min, that returns the simulation time in minutes. Okay, so please keep that in mind. The command clock min returns the simulation time in minutes. So if I want to get the simulation time in hour, I have to say clock hour. If I want to get the simulation time in seconds, I have to say clock second. So in the condition that I want to write here, I want to say, okay, get the simulation time. If simulation time is greater than or equal to 180, that means I'm here. I'm at 12 noon. And simulation time is less than or equal to 240. That means I'm between 12 to 1 during the lunch break. Also, I do not want to let any customers to come in. Not only that, but also I want to look at the simulation time. And if it's past 4 p.m., I also do not want to let any customer to come in. So if this condition holds, or if simulation time is greater than or equal to 420. Okay, so if these conditions hold, then send the customer to exit. Do not let them to come to the system. Else, let the customer to come to the system. Okay, so this condition will take care of this situation for us. All I need to do is to write this condition right at the point when the customer is at entrance. Once the simulation checks this condition, if I'm during the break time, that customer will not come to the system. If I'm not during the break time, that customer will come to the system. Okay, and everything is good for as long as I want to run the simulation only for 1 day, for 24 hours. Okay, however, if I'm planning to run the simulation for more than 24 hours, let's see what happens. I'm just going to let the simulation continue running, and then After the 24 hours of simulation are done, then we get to 9 a.m. the next day. Remember, we started the simulation at this point, which is time 0. So after 24 hours, when 24 hours are done in simulation time, we are 9 a.m. next day. Okay, that's where I am in the simulation next day. So at this point in simulation time, I'm at hour 24. Okay, that's the simulation time. In terms of the minutes, that's 1440 minutes. And then if I continue running the simulation, then at 12 noon in second day, the simulation time will be 27 an hour. So obviously 24 is just the start of the second day. After 3 hours in the second day, the simulation time is 27 hour. And in terms of the minutes, then I'm going to add 180 minutes. So from 9 a.m. to 12 noon, that's 3 hours. So that adds 180 minutes to this number. So in terms of the minutes, then it's going to be 1440 plus 180 minutes. If I continue running the simulation till I get to 1 p.m., then the simulation time will be hour 28. And if I want to write it in terms of the minutes, I'm going to add 60 more minutes to this time. So that's going to be 1440 plus 240 minutes. And then I continue running the simulation till I get to equivalent to 4 p.m. in the real world. And once I get there, in terms of the simulation time, I'm in hour 31. And in terms of the minutes, I'm in 40. So from 1 p.m. to 4 p.m., 3 more hours is added. And if I and that's equivalent to adding 180 minutes to this time. And if I do that, that's going to be 420 minutes. Okay. And let's assume I continue this till I get to day 3. And in day 3, again, I have 9 a.m., I have 12 noon, I have 1 p.m., and I have 4 p.m. And so when I get, if I continue running the simulation, when I get to 9 a.m. on the third day in the simulation time, already 24 hour is gone. Okay, so in the simulation time, if I have continuously run the simulation, when I get to 9 a.m. on the third day, simulation time has passed equivalent to 24 hours, one 24 hour for day 1 and another 24 hour for day 2. So the simulation time right at 9 a.m. on day 3 is going to be 24 hour, which is 1440 right here. Or in terms of the, so if that's in minute, if I was going to write it in hour, that would be 48 in hour. Okay, so this is the simulation time at the point that is equivalent to 9 a.m. day 3, which is after passing 24 hours. So in 12 p.m. On day 3, then the simulation time, I'm just going to continue writing the simulation time in terms of the minute. Because of this space, I'm not going to repeat it in hour as well. So in terms of the minute, if I want to continue running the simulation at this point, the simulation time will be whatever I have here, then which is 9 a.m. I'm going to add 180 minutes to it to get to equivalent to 12 noon on day 3. So the simulation time at this point will be 2 of 1440 plus 180. And when I get to this point, the simulation time at this point will be 2 of those 1440, which is 24 hours of the day before, plus 240 minutes. And if I come here to represent 4 p.m., on day 3, if I just look at the simulation time, which we have led to continue running, then the simulation time at 4 p.m. on day 3 will be 2:14:40 plus 4:20 minutes, right? So I basically got the time that I have here in simulation time at the start of day 3, and then I just added 180 minutes more to it because now I'm at 12 p.m. in the 3rd day, so that's 3 hours. This is from the start of the morning. Now at 1 p.m. I'm past 4 hours from the start of the morning, and 4 hours is equivalent to 240 minutes. And then at 4 p.m. I'm 7 hours past where I was at the start of the day. Okay, and 7 hours is equivalent to 420 minutes. So I added 420 to this number, which represents the simulation time at the start of the day in day 3. Okay, so as you can see, these numbers that I'm going to highlight are the ones that represent the simulation time. In day 1, day 2, and day 3 are the ones that highlighted in pink as well. Okay, so these numbers highlighted in pinks are actually the simulation time. If I'm going to let the simulation to continuously run over day 1, day 2, day 3, do not stop the simulation, then that's what I see as the simulation time. As you can see, the condition that I wrote here is perfect and works for day 1, because in day 1 it's meaningful to compare the simulation time with 180 and 240 and 420, which represents 12 noon, 1 p.m. and 4 p.m. However, as I go to day 2, then the simulation time is not comparable to these numbers. So for example, in day 2 simulation time, let's pick these numbers. Let's assume we are at this time in the simulation. So this number is equivalent to 16:20 minutes. Okay. Now, if I'm in day 2 and I'm looking at this time, then I tell, okay, look at the simulation time, clock mean. If it's greater than 180, okay, if it's greater than 180 and less than 240, okay, this time, this simulation time, which is 16:20, this time for sure is not less than 240. Okay, so although I'm at the break time, I'm at 12 noon, that's the start of the break time, but this condition that I wrote here no longer holds for the simulation time in day 2. So I cannot use this condition that I wrote here if I'm looking at day 2 or day 3, day 4, and so forth. So if I just let the simulation to continue running, then I cannot use this condition that I wrote here for day 2, day 3, or any day other than day 1, because this condition does not hold anymore for looking at the simulation time and checking if it's during the break time or past 4 p.m. Now, what we want to do is to see how we can change this condition, how we can rewrite this condition so that it's general and it can be used to check the simulation time not only in day 1 but also in day 2 and day 3 and so forth. Okay, so to be able to do that, first let me review a function that you guys already know. That's the modulus function or mode function that you all know. So if for example I write 10 mode 2, what this function is going to return is to divide 10 by 2 and return whatever we have as the remainder. Obviously here the remainder is 0, right? If I divide 10, to look at 10 mode 3, so here basically it means divide 10 by 3 and then return whatever we have in remainder. So in 10 there are 3 units of 10 and there are 3 units of 3, and then we have 1 unit as the remainder. For example, if I have 20 mode 6, then in 20 I have 3 units of 6, that's 18 units, and then whatever is left at the end is 2 units as the remainder. Okay, so mode function returns when we have number A, mode number B, it divides A by B and then returns whatever we have as the remainder. That's the result of the mode function. Okay, so also if I have scenarios like this 6, so if I have 6 mode 20, and then here the result is going to be 6. How many 20 units are in 6? None. So what is the remainder? Is 6. Okay, so pay attention to this type of writing this mode function as well. Okay, so I'm going to use this function to see how I can modify the condition that we wrote here to be able to run the simulation not only for 1 day, but also for day 2, day 3, and so forth. If I want to continuously run the simulation, for example, for 5 days, to consider what happens in 5 days in this call center or in this bank. So to be able to do that, instead of just looking at the clock, which is the simulation time, I'm going to look at add clock mode 1440. Let's see what happens here. If I'm at day 1 and I look at this function, let's assume in day 1 I'm somewhere, let's assume I'm somewhere here, okay, and that's equivalent to minute 100, let's say. Then the simulation time returns 100 mode 1440, and that is going to be 100. So that's basically simulation time 100. Okay, let's assume I'm somewhere here in the break in the first day, and let's assume I'm in minute 200, right? That's obviously between 180 and 240. Let's assume I'm in minute 200 and I write 200 mode 1440. So this operation returns 200 to me. Okay, I'm still good. The simulation time is 200 and I still get 200. And I'm good to use this condition. Still I can say, okay, I'm 200, I'm greater than 180, and I'm less than 240. So it's break time. Do not let any customer to come to the system. Okay, let's assume I'm somewhere here in this range, and let's assume I'm in minute 300. Okay, falls between 240 and 420. So 300 mode 1440, that returns 300, right? So then I'm still good. The simulation time is 300 and I get 300, and I can compare the 300 with the conditions here that I wrote here, and the 300 is in the operation time. So then the condition works, then the entity will come to the system and it will work. And let's assume I get to somewhere past 4 p.m. Let's assume I'm in minute 500, that's past 4 p.m., right? And I write 500 mode 1440, and that returns 500, and that's still good too, because 500, if I look at this part of the condition that I highlighted here, 500 is greater than 420. That means I'm past 4 p.m. So the simulation does not let that new customer to come to the system. Okay. So this line that I wrote here, instead of just simply looking at the clock, which returns the simulation time, if I look at clock mode 1440, this still is good and still is working for day 1, as you saw, because I still get the times that I want for day 1, and still I can do my comparisons and everything work. Okay, let's see what happens if I go to day 2. I have the simulation times that clock is going to return to me, and I want to see what happens if I still use this function here. Okay, when I go to day 2, in day 2, let's assume I'm here, somewhere here. Let's assume I'm here, somewhere here, And this is the start of day 2. The simulation time is 1440. The simulation time is 1440. And let's assume I let 100 more minutes passes from 9 a.m. in day 2, and then I call the simulation time. And then I'll call the clock, right? So when I call the clock, as you can see here, the clock returns the simulation time. And let's assume I'm 100 minutes into the day 2. So the simulation time is going to return 1440 plus 100. And I'm going to still use mode 1440. Okay. So what do I get out of this? This will return 100 for me, right? So 1440 plus 100, whatever that number it is, mode 1440 will return there is one 1440 inside this time. So that will be removed. Then whatever is left is 100 as the remainder, and that's going to be returned to me. And let's assume in day 2, I just let the simulation time to continue running, and I'm somewhere here. Let's say I'm at 1440 plus 200. Remember, in day 2, this is the time that represents 12 noon, and this is the time that represents 1 p.m., right? So if I put 1440 plus 200, that's between this time and this time. That means I'm somewhere between 12 noon to 1 p.m. in day 2. And if I just call that number, 1440 plus 200 in day 2, mode 1440, then obviously that is going to return 200 for me as the remainder, right? And then if I'm going to still keep the condition the way that I wrote it here on the top, if I replace the clock mean by this expression that I wrote here, I can still, although I'm in day 2, but I can still compare that minute with 180 and 240. Because now, although I'm in I'm in day 2, and the actual simulation time is 1440 plus 200, but this function is going to return 200 to me, as if I'm in day 1, and this is just 200 minutes from the start of the day, which would fall somewhere in the break time. And if a customer comes during that time, I'm going to send that customer to exit. So this mode 1440 that I wrote here, this 1440 is equivalent to 24 hours in minutes, right? 1440 is equivalent to 24 hours in minutes. If I multiply it by 60, that's so this mode function that I wrote here basically says, look at the simulation time and take away whatever complete 24 hours is in it and return whatever is left. So here we look at the simulation time in day 2 and we take away whatever complete 24 hour is in it. There is one complete 24 hours, which is 1440 minutes. We take that out and then we look at the remainder, which is 100 hours or 200 hours. And if I just do that, the same thing for day 3, in day 3, whatever time that simulation time is going to return to me will be in this format, right? These are the simulation time. And as you can see, they are already 2 complete 24 hours plus something. So when I write this as this time, which is the clock simulation time will return something like that. So when I write those as mode 1440, then the simulation, then this line of code will first take out whatever complete 1440 minutes I have in the simulation time that's how many complete 24 hours is in the simulation time. And here there is 2 of them, because that's day 3. That's obviously in day 1 and day 2, we have had 2 complete 24 hours. It takes that one out and then return whatever is left as the time of that specific day. Okay, so basically mode 1440 works like a reset time. When I'm in day 2, when I use mode 1440, puts away whatever 1440 units I have in day 2, and then returns whatever is left, which is like as if I reset the simulation time and start again from 0, and then go to minute 180, minute 240, minute 420. So that way I can just keep this condition the way that I wrote it, and I still can compare the simulation time with 180, 240, and 420. So to be able to do that, then I have to change my condition, and instead of just looking at clock, the simulation time, I have to look at clock mode 4040. Okay, so I have to look at this and compare that with 180 and say that, okay, if this holds, if this condition holds, and or then so if this condition holds, meaning that if we are during the break time or past 4 p.m., then send the customer to exit. Otherwise, let the customer to enter. So that way, I don't need to worry if I'm in, if I just let the simulation to continue running, and if I'm in day 1 or day 2 or day 3 or so forth. So if I use this function, instead of just looking simply at clock, the simulation time, if I look at the clock mode 1440, at any point of time, this will return the number of hours in that specific day. It will take away whatever 24 hours, complete 24 hours I have in the simulation time, and treats that day in which we are in simulation, okay, as if we reset the simulation time counter in every day. Now let's go back to the simulation and write this logic in ProModel. Okay, so right here, when the customer comes to the entrance, we have to write the code and check the simulation time, and if we are during the break time or the past 4 p.m., we should not let the customer to come in. So if clock in minute mode 1440 is greater than or equal to 180, and clock mode 1440 is less than or equal to 240. And let me put this whole thing in a big parenthesis. So if this condition holds, or clock min mode 1440 is greater than 420, greater than or equal to 420, which means you are past 4 p.m., then we do not want to let any customer to come in. So if we do not want to let the customers to come in, if we do not want to let the customers to come in, that means we are going to set those customers to exit. So set the customers to exit. Okay, so in the first line, I remove whatever we had in the destination. So if this condition holds, which means I'm during the break time or past 4 p.m., I do not want to let the customers to come to the system. So the customers go to exit. They have to go to exit. So this line I can refer to by calling it as route 1. It has the block number 1. It's referred to in ProModel as route 1. So if here in this line of the code, I want to tell the simulation go to this line, I say, okay, go to route 1. Okay. Okay, so if this condition holds, then go to route 1, block number 1, which send the customer to exit. Else, we want to let the customer to come in. And if I want to let the customer to come in, that's another destination. That means let the customer to come to the system, and the customer goes to the teller queue. And if I want to refer to this line to send the customer to this line, I have to have a different block number for this line. And if I want to have a different block number for this line, I have to click on the rule. Here you see start new block. I have to check start new block and then press OK. And then this line gets a new block number. That's block number 2. So now I can refer to that as route 2. Okay, so that's block number 2. So when I say route 2, the simulation goes here and finds a line or that has a block number 2, and then it's going to run this line. So when we are going to when we are going to call or tell the simulation to go to this line or that line on the destination part using the codes that we write here on the operation, we always have to call them by route numbers, and we have to give us different route numbers to different lines if you want to send them to different lines. And as I said, to be able to give these lines different numbers, all we need to do is to click on the rule and then say start new block, and then it's going to give a new number to these blocks. Just pay attention that you should not do this for some other scenarios. For example, for inspection, when we inspected the parts, then the part on the destination could go on to the mill rework or to the grind rework or to the scrap part or exit the system. In those scenarios, I said make sure all these possible destination, all of them are part of one block. In those scenarios, they should not have different block numbers. In those scenarios, all of them should just have one number, which is the first line, which has number 1. The rest should not have any block number. Only and only when we want to refer to these possible destinations as different routes in the codes that we see here, we give different block numbers to them so that here I can call them as route 1, route 2, route 10, and so forth. Only in this scenario, we need to give different block numbers to the lines that we specify here. Let's run the simulation for 140 hours. So this 140 hours is equivalent to running the simulation for 1 month, for 1 working month continuously in the real world. Why? Because this bank worked from 9 a.m. to 4 p.m. That's 7 hours working each day, and each week has 5 working hours, 5 working days. So in each week we have 35 working hours, and then in a month we have, let's say, 4 weeks, and that's going to be 4 multiplied by 35, and that's going to be 140. So if I just let the simulation to continue running for 140, that's equivalent to the scenario that I run this simulation or this bank for 1 month without stopping the simulation time. So I want to see if I look at just how this bank is performing in 1 month, how many customers are getting processed, and so forth. We're going to run the simulation. Okay, so about 2,800 customers got the service and left the system in that time, which is equivalent to the customers that were processed in this bank in 1 month during the working days and working hours. And the customers that enters the system, they spend about 7 minutes or so in the system, which is a good amount of time. And then, yeah, we see how our operators were busy and so forth. Let's go back to the model. So here, if I ask you to count how many customers got rejected during the non-working hours, then all you need to do is to define a variable. Let's go here. We call this variable as customer rejected. Okay, so let's call this variable as customer rejected, and let's go back to the processes. So my goal is to count how many customers got rejected. They could not enter the system, and the customers get rejected and they cannot enter the system only if they enter during the lunch break or during the time that the bank is closed at night after 4 p.m. till 9 a.m. next day, right? Only is in those scenarios we reject the customer and send them to exit. So if I want to count number of customers that got rejected, I can increase that variable right here in the move logic. So when the customer gets rejected, it's during the break time or after 4 p.m. and the customer goes to route 1 right here. When the customer is sent to exit right here, I can just increase. I'm going to write it in the move logic. I can just increase this variable that counts number of customers that get rejected. So that way, this variable, every time a customer is sent to exit because of this condition, is going to get increased by 1. And remember, that's not the exit when we go from operator to exit. We are not going to increase number of that variable when we get to exit from the operator. That's not going to happen. We are going to increase that variable customers rejected when we go to exit from the entrance. If from the entrance directly I go to exit, that means I got rejected. I could not enter the system. Okay, and also pay attention that here in the operation, there is no specific order between the lines that you write here. I could write the first line to be the second one and the second line to be the first one. There shouldn't be any specific order between here. As long as you refer to the right line in your code here, that's all that matters. When you want to send the customer to exit, just make sure to come here and just see which line is the one that send the customer to exit and just call that line. Here it happens to be the first line, so I'm going to call it route 1. If it happens that for you the second line is the one that sends the customer to exit right here, then call route 2 because that's the one that sends the customer to exit. Just because in your logic this is the condition for sending the customer to exit, and that is performed right here.